application of integrated rate laws leads us to talking about half-lives. Half-life is the amount of material it takes for half of a material to disappear. Well, probably the most well thought out and obvious example of half-life is when it comes to nuclear reactions. How long does it take for half of the nuclear material to disappear or transform? Well, all nuclear reactions obey first-order kinetics. This is something you're going to want to remember for the next chapter. All nuclear reactions follow first-order kinetics. So we can examine the half-life of something like uranium, which takes millions and millions of years to undergo a single half-life, and we can actually figure out what that half-life is using the first integrated rate law. Now what I've got here is the deriving of the half-life for a first-order reaction, and what you see is that the half-life of the reaction is equal to 0.693 divided by the rate constant K. How did we get the rate constant K? Well, for a nuclear reaction, we just measure the decay of a material over the course of several months, and then we know it obeys first-order kinetics, so we can fit it to a line, get the slope of that line, and then see how long it takes any nuclear isotope to decompose. In a first-order half-life process, the concentration does not play a role in the half-life. I'll say that one more time. For a first-order process, the half-life is not concentration dependent. If, however, we go through the same derivation for a second-order reaction, what we find is that the half-life is dependent upon the initial concentration of whatever reactant was present. So half-lives can be concentration dependent for second-order processes, but they are not concentration dependent for first-order processes.